Okay, guys, inequalities are back. I'm sure you all loved them in Unit 2. I'm sure you've been missing them. So, we are now looking at rational inequalities, and by the end of this lesson, you can solve rational inequalities algebraically and state restrictions on the variables. So, in Unit 2, we looked at how we can solve inequalities with technology first and then without. And the only reason we do that is so that you guys can really visualize like what an inequality means, what the question's actually asking for. But ultimately, we need to be able to do this without technology. So we will use technology throughout this lesson to check our work, but it will not be the method that we rely on. And on a test, you need to be able to show all of your work algebraically. So just to recap, when solving an inequality, we want to isolate everything to one side. So in this case here, we would be subtracting 3 from both sides so that we're left with x squared plus 3x minus 10 is less than 0. Now ultimately this is asking me, when will this quadratic have function values that are less than 3? That's what the inequality is asking. But it's easier for us to isolate everything and create a new polynomial and a new inequality that now says, when will this polynomial be less than 0? And the reason that that's easier is because if we can factor, this is a quadratic that opens up, and let's just say that it looks something like this. We now know it is less than 0 when it is below the x-axis. So it becomes really easy for us when we are solving inequalities with 0 on one side. Sorry guys, it's photo day here, so we're getting a lot of interruptions. Okay, so what we are left with is a simple trinomial here. And so we're going to look for two numbers that add to positive 3 multiply to negative 10. So we're going to have x plus 5, positive 5 minus 2 is positive 3, positive 5 times negative 2 is negative 10, and we want to know. And the result is a intercept at x equals negative 5 and an intercept at x equals positive 2. So my drawing is not accurate for this particular polynomial, but that's okay because I want to use the number line method anyway because that's the one we're going to rely on for this. So when we have our number line, these are what we would call our points of interest, and they are our intercepts. And the reason there are points of interest is because the intercepts are the locations where the function may change from positive values to negative values to positive values. That happens at intercepts for polynomials. So when we put these on the number line and we say, okay, negative 5 is over here and positive 2 is over here, and some of you are putting 0 on your number line, just be careful because we do not need to investigate what's happening between negative 5 and 0 and between 0 and 2. We only need to investigate what's happening beyond the intercepts and between the intercepts. So we have to figure out, well, what's going on when x is less than negative 5? What's going on when x is between negative 5 and 2? And what's going on when x is greater than 2? And we do that by investigating, and I strongly recommend you investigate from your factored form. So you might say, okay, well, something that's less than negative 5 it doesn't matter anything because at negative 5.1, if the function is positive, it's going to stay positive for all values because there's no other x-intercept. It's never turning around. So you choose anything you want that's less than negative 5. So let's just choose negative 10. Sounds like a nice number. So if we subbed negative 10 in, negative 10 plus 5 is still going to be a negative. Negative 10 minus 2 is still going to be a negative. We have a negative times a negative, which is a positive. So on this interval from negative infinity all the way up to negative 5, this function will have positive function values. Between these two is 0. Love when that happens because subbing in 0 makes it easy. So 0 plus 5 is a positive. 0 minus 2 is a negative. We have a positive times a negative, which is a negative. And then over here again, we sub in anything we want. Sure, let's sub in 10 as long as it's greater than 2. So when we sub in 10, we have 10 plus 5, which is a positive. We have 10 minus 2, which is still a positive. We have a positive times a positive, which is a positive. Now the original inequality said, when will all of this be less than 0 and not equal to 0? So we don't want to include these points. So therefore, we'll just call it f at x. F at x is less than 0 on the interval -5 to +2, and not inclusive of either of those points because it's equal to 0 at those points. Okay, so a really quick refresher of how we do this, because the method's going to be the exact same with one minor addition for rational functions. And what that is when we're solving rational inequalities, we do the exact same thing, isolate everything to one side, leaving 0 on the other. And in polynomial inequalities, which is what we just looked at, we solve to determine the x-intercepts because these are the locations where the function might, doesn't always, but might change from being above or below 0 and vice versa. So I want you to think about, when might a rational function go from having positive function values to negative function values, or vice versa, go from having being above 0 and below 0. So if we think about a rational function, let's just draw a sketch of one. And let's say that it looks like this, and like this, and whoop, we'll come to that after, and like this. So where does this function, actually no. Let's go like this, just for funsies. And that's not a great example of a rational function because of the intercept. One last time, like this. Okay, so when does this function change from positive to negative? Well, it's positive, 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 and then we reach a vertical asymptote. Then all of a sudden on the other side of that vertical asymptote, it's negative, 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 negative. We reach an intercept, positive, 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 positive. We reach an asymptote, still positive. So a rational function has the possibility to change from positive function values to negative function values as you cross both vertical asymptotes as well as x-intercepts. Polynomials is just the x-intercepts that we have to examine as our points of interest. But when we're looking at a rational function, we have to also consider the vertical asymptotes because that's the point where it may change from positive to negative, and it also may not, okay? So let's look at this here, and I want you to, in a second, pause the video and actually solve this polynomial, that should say rational inequality, solve the rational inequality below. So this graph here represents the rational function f at x. Okay, so this is f at x. And the inequality is asking, when does f at x, or when is f at x less than or equal to 0? So we're just looking out from a graph, and it's really important that we can read when that's happening. So when is this function less than 0? Well, it's less than 0 all through here. Then it's above 0. Then it's less than 0 from here, and then that's it. It's not less than 0 again, not from what we can see. So there's two intervals where this polynomial is less than or equal to 0. So the first one happens forever and ever and ever this way. So from negative infinity all the way up until here, which is where we have a vertical asymptote, and that is at -1, -2, -3. So from negative infinity all the way up to -3, and not at -3 because it's not equal to anything at -3. So it's going to be a round bracket because that's a vertical asymptote. And then again, less than or equal to 0. It's actually equal to 0 right here, which is at -1. So this time it's inclusive of -1, and then forever and ever, ever only up until we reach the next vertical asymptote, which is happening at +1, and it can never have a function value at +1, so we can't include +1. So that's like even just writing that is a bit tricky. You have to know the start and end of your intervals, and you really have to know when is it inclusive of that point and when is it, or sorry, inclusive of that point and not inclusive of that point. So this is the solution to this inequality for when this function f at x is less than or equal to 0. So now, of course, and when you go through the practice, there are questions just like this where you're just being able to read the graph and work on that interval notation, or if you're using inequality notation, that's fine as well. So do make sure you do the practice, but of course, we are going to look at solving this algebraically. So what is important is that we have to consider what is happening on either side of all x-intercepts. That's old news. We used to do that with polynomials. But now what is new is we also have to consider what's happening on either side of all vertical asymptotes. Because vertical asymptotes is where the function has the possibility to change from positive to negative function values. A horizontal asymptote, if we have a horizontal asymptote here, like even if the function crosses it or not, nothing happens. It was positive, it's still positive. Like, so we don't have to consider our horizontal asymptotes, but we do have to consider our vertical asymptotes as now a point of interest. Okay, so vertical asymptotes and x-intercepts, both of these are our points of interest. And when we put them on our number line to do our investigation, we have to consider all x-intercepts and vertical asymptotes. Okay, so here we have solved the following rational inequality by sketching, and here is actually a sketch. So there might be times where we are sketching. So here we have 2 over 3x plus 7 minus 4. Now, in order to solve this, we need to combine these two things into a single inequality. We could, a single rational function. We could add 4 to both sides, but then how would we know when exactly 2 over 3x plus 7 is going to be less than 4? It would be tricky. And so what we want to do is just combine these into a single rational function, and the way that we do that is using a common denominator. I need this to have a common or a denominator that's common with this, so I need to have 3x plus 7, on the bottom, which means I need to multiply the top also by 3x plus 7. So I have 2 minus 4 times 3x plus 7 all over 3x plus 7. I can now combine these because they'll have a common denominator, and I want to know when that rational function is less than 0. So I distribute my negative 4 here, and I have 2 minus 12x minus 28 over 3x plus 7, and I want to know when that is less than 0. So now I can combine. I have 2 minus 28, which is negative 26. So I have negative 12x minus 26 over 3x plus 7, and I want to know when that is less than 0. So what I have is a linear over linear rational function. So if you can recall back to I think it was lesson 3, where we looked at linear over linear. Now remember that we're interested in two things, okay? So I'm just going to write this. We are interested in only, actually no, I guess because we're graphing it, we need all of it. We are interested in particularly though the vertical asymptotes and the x-intercepts, because that's where our function might change from positive to negative. So when will this function have a vertical asymptote? Well, vertical asymptotes occur at the x values that are not allowed. So there will be a vertical asymptote for whatever x value makes 3x plus 7 equal to 0, because we can't divide by 0. So we use our inverse operations and we figure out that there will be a vertical asymptote at x is equal to negative 7 over 3. And because we are trying to graph, you may be interested in converting that to a decimal just to graph with a little bit more accuracy, but I would make sure you have it as a fraction as well. So that's negative 2.33 continuous. And I've already have this graph here, but just to kind of show you guys. So we've got, this is negative 10, by the way. So this is going up by, this is negative 2, negative 4, negative 6, negative 8. So negative 2.33 is where we have that vertical asymptote, which is what we see happening here. So let's put that on our graph. And I should have just covered this so you couldn't see it right away, but we've got a vertical asymptote just past Oh, that's funny. That's what happens when I draw a straight line. Just past that negative 2. So somewhere around here we have that vertical asymptote at negative 2.33. Okay. X-intercepts happen when the numerator becomes 0. 0 divided by anything is just equal to 0. So if we can figure out when will negative 12x minus 26 equal 0, we can figure out our x-intercepts. So we have negative 12x is equal to positive 26, and we divide by negative 12 on both sides, and we end up with x is equal to positive 26 over negative 12. We divide top and bottom by 2. We end up with negative 13 over 6. So that would be our fraction. And then again, if we wanted for graphing, negative 13 divided by 6 is equal to negative 2.166 continuous. Negative 2.16 continuous. So that is the location of our x-intercept. So here we have an x-intercept there. And here we have a vertical asymptote. And those are two really important locations on our graph. So again, we would label our x-intercept, and they're really, really close together here. In fact, this asymptote is just a little bit too... Oh, my video got paused. I think I know why. Every time I go to Desmos and I hit... Anyway, so... Okay, what I was saying was if I put this function into Desmos, if I don't want to use my calculator to sub in some of these values, I can sub in to the left of that vertical asymptote and I get a negative function value, and I can sub in to the right and I get a positive function value. So when I go back over here to the left, I had a negative function value, and to the right I had a positive function value, or in other words, on the left side, so we could say as x approaches negative 2.33 from the left, remember, continuous from the left, the function f at x approaches negative infinity, and as x approaches negative 2.33, the vertical asymptote from the right, the function f at x approaches positive infinity. And so when we go back to our graph, we would say on the right-hand side of that asymptote, we're approaching positive infinity, and on the left-hand side of that asymptote, we're approaching negative infinity. And now, because of our asymptotes and our x-intercept, we have enough to draw our graph. And ultimately, all of this was asking us, when is this function that we just graphed less than 0? So I'm going to get rid of those lines just because we have the purple curves, which are a lot neater. And so when we finally had our graph, we would be able to look at it and say, okay, this function is below 0 from negative infinity all the way up until negative 7 over 3. Then at that vertical asymptote, it goes above 0, but only until the x-intercept, and then it drops back down below 0 all the way until positive infinity. So our solution, just to write it up here so it's beside our graph, and ultimately, like, we wanted to know when the combination of these was less than 0, but let's just jump here and call this f at x and say, therefore, f at x is below 0 on the intervals negative infinity all the way up until, that was our vertical asymptote, which was negative 7 over 3. And we do not want to include that because it's a vertical asymptote, so open bracket. And then again, it becomes positive for a little while on the right-hand side of that or the vertical asymptote, but then at the x-intercept, which was 13 over 6, negative 13 over 6, yeah. So at that point, it drops back down below 0, and it stays below 0 all the way until positive infinity. And this is not inclusive, even though it is an intercept, because we can never include our vertical asymptotes because they're values that are off limits. We could include an intercept, but only if it asked you when is this function less than or equal to 0. It's equal to 0 right there, but we don't want to know when it's equal to 0. We only want to know when it's below 0, so we don't include that intercept as one of our solutions. Whew. Okay. What time is it? That's 19 minutes already. There's your solution, and that was solving it by sketching. And what we know is that sketching these functions takes a good amount of time. So now let's look at the following inequality using a number line and interval test. And so again, in order to use the number line approach, we have to have a number line that has all of our points of interest on it. And that's just such a ridiculous looking number line. Oh, what have we done here? So let's draw one and actually make it straight. Okay, so the points of interest that we are interested in are the x-intercepts and the vertical asymptotes. Those are the spots where the function may change from positive to negative. So this function is going to have vertical asymptotes when x minus 7 is equal to 0, which is at x equals positive 7, and also when x minus 2 is equal to 0, which is when x is equal to positive 2. So we're going to have vertical asymptotes at positive 2. Let's put the 2 here, and again at positive 7. And then we also need to investigate the x-intercepts. So x-intercepts happen when the numerator equals 0, because at x-intercepts, that is when your f at x is equal to 0. The only way to get a function value of 0 is if you're doing 0 divided by something, because something divided by 0 is a vertical asymptote. That's an error. So the only way to get back a function value of 0 is if the top ends up equaling 0. So we want to figure out, well, when, because if this is multiplication, if x plus 3 becomes 0, the whole numerator becomes 0. So when will x plus 3 equal 0? Well, that will happen when x is equal to negative 3. And when will x minus 4 equals 0, that'll happen when x is equal to 4. So we have another intercept here at 4, and then we have another one over here at negative 3. So these are intercepts, and we want to know when it's greater than or equal to. So it is equal to 0 at these points. These are vertical asymptotes, so we're going to put open circles there, okay? Okay, sorry guys. So these are my vertical asymptotes, so my function is not equal to 0 at these points, so I just put those open circles because I want to make sure when I write my intervals I don't include those values. And now, just like when we were doing inequalities of polynomial functions, I have to investigate what is happening in between each of these points of interest as well as beyond the points of interest. So this is that tedious part where we have to sub in some values. Anything that is less than negative 3, so we could look at negative 4. And this, I gave you a rational function already in factored form, but anytime you're solving for vertical asymptotes and x-intercepts, you have to factor the denominator to find your vertical asymptotes, and you have to factor the numerator to find your x-intercepts. So you may as well rewrite your polynomial in factored form. It is so much easier to sub into this than it is the standard form. So when I sub in negative 4, I have negative 4 plus 3, which is still a negative. Then I have negative 4 minus 4, which is also a negative. On the bottom, I have negative 4 minus 7, which is a negative, and I have negative 4 minus 2, which is also a negative. So I have a negative times a negative, which is a positive, divided by a negative times a negative, which is a positive, and then I have a positive divided by a positive, which is a positive, okay? Now I have to choose something between negative 3 and 2. Anytime we can choose 0, we might as well. So I've got 0 plus 3, which is a positive, 0 minus 4, which is a negative, divided by 0 minus 7, which is a negative, and 0 minus 2, which is a negative. So I have a positive times a negative on the top, which is a negative, and a negative divided by a negative on the bottom, which is a positive, and ultimately I have a negative divided by a positive, which is a negative. So we're negative on this interval. Now we need to investigate here, here, and here. So we've got 3 more. So let's choose 3 for that interval. 3 plus 3 is positive. 3 minus 4 is negative. It is negative 1, but negative is what we need. 3 minus 7 is a negative, and 3 minus 2 is a positive. So I've got a positive times a negative, which is a negative. I've got a negative times a positive, which is a negative. A negative divided by a negative is a positive. And then over here, I'm going to sub in something between 4 and 7, so let's call it 5. 5 plus 3 is positive. It's probably neater to write it without the brackets. 5 minus 4 is still a positive. 5 minus 7 is a negative, and 5 minus 2 is a positive. So I've got a positive times a positive on the top, and a negative times a positive on the bottom, and positive divided by a negative is a negative. And we could probably predict what's going on over here, but we can't make any assumptions. You know what they say about assumptions. So we sub in an 8. 8 plus 3, that's positive. 8 minus 4, also positive. 8 minus 7, also positive. 8 minus 2, also positive. So I've got a positive divided by a positive, which is a positive. And believe it or not, I know some of you didn't love this number line approach for polynomials, but I actually find it easier for inequalities. And then again, we always go back and say, okay, what was this question asking me? Let's call this entire function f at x. And ultimately, we were trying to figure out when is this rational function f at x greater than or equal to 0. So the intervals where it's greater than is here and inclusive of this point, not inclusive of this point, but inclusive of this point. And then again, not inclusive, and then all the way to positive infinity. So there's 3 different locations where this rational function is greater than 0. So therefore, f at x is greater than or equal to 0 on the intervals negative infinity all the way up to negative 3, inclusive of negative 3. And then again, from 2, but not inclusive of 2, all the way up to positive 4. Oh, I didn't write the 2 there. 2 up to positive 4 and inclusive of positive 4. And then again, from positive 7, but not inclusive because that's a vertical asymptote, all the way up to positive infinity, and our infinities are never inclusive. So there is your solution for that. And this is about as easy as it's going to get because I gave you the polynomial in factored form first. So once again, this video is getting a little long. I'm going to put another example up here where you have to combine these 2 inequalities into a single inequality, and then from there you will have to determine the location of any vertical asymptotes, x-intercepts, use your number line approach. I'm going to stop this video, and then the second video will just have the solutions for this particular example. So please do try this one and then come back for the next video to check your work. Your practice questions are here, not the Nelson textbook, but page 184, numbers 4, 5, 12, and 9.